welcome back. In this video, we are going to look at an introduction to linear regression. If you have seen linear regression before, this will just be a repetition for you. But we are going to do this in the context of inverse problems. As you know, the theme of this week is linear models for inverse methods in heat transfer. So I'm just going to repeat a brief context of this problem that I did in the previous video also, just quickly. And then we will come back to how linear regression is relevant to this. And then we will look at some details of linear regression here. So recall this problem that I had shown before about the inverse problem within a slab. So for example, you could consider this slab here. And let's say it has a few thermocouples. Here we have taken 6 uniformly placed thermocouples within the slab. And let us say we know the length of the slab. We also know the thermal conductivity. And we have some measured temperatures here, okay, at these positions, at these specific positions. And we want to find out what the temperatures on the left and right are. So this, as I had labeled last time too, so we are going to call this T0 and TL. Suppose we don't know what these are. This, as I said in the previous week, is an example of an inverse problem. So this is what we wish to figure out. And once, of course, you can figure out T0 and TL, you can also figure out the heat transfer. Okay, so this too, let's say we do not know. Okay, given the thermal conductivity. So that you know from simple basic forward heat transfer. Now, what makes this problem relevant or slightly difficult, as we had discussed earlier, is the fact that the solution is not unique. So as we had discussed earlier, this non-uniqueness is a feature of inverse problems. Okay. Why is the solution non-unique? This should be fairly clear when we look at the actual plot. So if we look at this plot, the circles here are actual measured temperatures. Okay, so these circles here are measured temperatures. Okay, so these points here refer to measured temperatures. And these x's, of course, are our locations. So at these locations, we have some specific measured temperatures, but we want to figure out what the temperature at the left and what the temperature at the right would be. And depending on what fit we choose, suppose we choose this fit as linear, then you get a different measured temperature. And if you choose this, you get a different measured temperature. All of us can see that probably somewhere like this is what we would call the visual best fit. Okay, so this one looks like the visual best fit. This is what looks the best. But is that all? Can we have a more mathematically nicer way of putting this? So the question really is, what is a mathematically sound way? To define the inverse problem. Now I'm going to just mildly set up the inverse problem in this video, and in the next video we will actually discuss a formal way to set all inverse problems. But for this video, the purpose is to just motivate this inverse problem, quickly look at linear regression and see how relevant it is, and then move on. Okay, so the purpose here is to just set up the linear regression problem and give you a quick solution which you would be familiar with from school days. Okay, now once we do that, the point here is that the forward model for this problem. So the forward model is going to look like this. Given left and right temperatures, find temperatures at the thermocouples. Okay, so as I discussed in the previous video too, suppose I give you T0 and TL. Can you find out T1, T2, T3, T4, T5, T6? Okay, which we can, and we already saw that the forward model looks like T equal to some function of X, which is linear. Okay, the explanation was there in the previous week. So now we want to go and do the reverse model, which is given these 6, can you find out T0 and TL? And as we just saw, the solution is non-unique. Which one of these fits should I choose? If I choose this, I get a different T0 and TL, and this, I get different T0 and TL. But notice one fact, we are using the physics. Where do we use the physics? We use the physics for the forward model, which we will use in the rest of the video. Okay. So this is a model, and the physics says as follows. The physics says temperature. I'm going to put a hat here. The hat denotes a model. So temperature is something, some parameter plus some other parameter times X. This information comes from the physics of the problem. Okay. So notice this, since this problem is linear, or this equation is linear, we call this a linear model. And we will deal with the fact that linear models themselves can be extremely powerful, and we will deal with those both this week as well as the next week. And in the subsequent weeks, we will see how to move on to nonlinear models. Now, some of you might think, what happens in case I have no direct information from the physics? Suppose I have a turbulence problem. We know that no such formula is forthcoming. What do we do in such cases? So we have several options. One of those options is machine learning, which we will be covering towards the end of the course. So the progression is as follows, as far as the course is concerned: linear, then we use linear and non-linear. And as you will see, we will use this ideas that we have developed in non-linear to build machine learning and neural network models. So this is the hierarchy of models. As you will see, even these are reasonably simple models. We will look at more complex models within the final week of this course. I will just give you a brief introduction, but that would lead you to state of the art. Okay, so let's now come to this linear model. If you observe, all we have done is as follows. We have made a table. So X here is the location. So I have multiple locations, X1, X2. I went till X6, but let's say in general, we go till Xm. Okay. So where M is the number of data points. Similarly, I have Y. Y, let's call this the ground truth. Now, this is not a language that is used as a standard language within the inverse methods community, but this is a standard language which is used within the machine learning community. I am going to stick with it because I expect that as you go further and further in your career and you use these methods, that you will encounter machine learning more and more. As you can see, it is getting more and more common within science and engineering to see this. So I'm going to use this word ground truth. If you wish, you can say this is the experimental measurement. Okay, so the measured temperature, which I'm going to call Y here. Y would be any variable that we measure, but in this specific case, this is temperature that we are measuring. So we have, let's say, Y1, Y2, so on and so forth up until Ym. So the mth location has a temperature Ym. The third thing that we all carry is Y hat. This is what comes from my model. Now, suppose my model is W0 plus W1x. For each value of W0 and W1 that I guess, I will get a different value for, let's say, if I take at 0.04, even though the truth is somewhere around 12 point something, my model, depending on what values I choose for these parameters, it might give something like 9, or it might give something as high as 15. So this value here, Y hat, is the model value, okay, or the model prediction. We denote the fact that it's a prediction by this hat on top. Okay. So similarly, at each point, once you know the model parameters, you will get some predictions here. So these predictions will look like Y1 hat, Y2 hat, so on and so forth up until ym hat. All right, so you can see all that reflected in the picture here. So this is for this model, this is y hat. For this model, this is y hat. And this, of course, is y. Okay. So in this case, this is y4 hat for some model, and this is y4 hat for another model. In general, y and y hat will not match. Okay, so that's the thing that we can notice. I'll write that down. In general, y is not equal to y hat. But another thing is true in general. We want a great model. So the best model would be such that y equal to y hat for all measurements. Now we will see later on in this course that this need not actually be the best, but we have an intuitive sense that in case you are able to get your prediction to match the truth. So remember, y is the truth and y hat is the prediction. In case the two match for every single measurement that you make, it looks like you have actually got a great model. So what we want is as follows. We want a model that minimizes the gap between truth and model. Okay. So we want some measurement of what the gap between the truth and the model prediction is. And the way we go ahead and do that is to define a new quantity. So we define this quantity called r prime square. Okay, I'll tell you why it is called r prime square shortly. So this is a summation of the gap between yi and y hat I square. Okay, sum of the square divided by something I'm going to call sigma I square. Okay. This goes from I equal to 1 to the number of measurements m. Okay. What does this mean? Okay, so if we go back here to this picture, let's take the model below. Okay, so this is, let's say, model 1. It looks like a bad model, but let's take this model. So if we take this model 1 and we look at this gap, the prediction is so much, the temperature is so much here. There is a gap between the two. You find the gap, square it, and then divide it by some sigma 1 square. Okay. Find this gap, square it, divide it by sigma 2 square, find this gap, so on and so forth. Now, what are sigma 1 and sigma 2? So what these are is they are measurements is the variance. I'll mention this more when we come to the statistics part of this course. So right now, let's just say accuracy of the sensors. So going back to our example, if we come here, we made these 6 measurements at these 6 points. Now, it doesn't mean that each one of these sensors, some of these might be old, some of these might be new, some of these might be more modern, some of these might be more expensive, so on and so forth. So each one of these would have a different accuracy. So in general, this one could have an accuracy, it's like sigma 1, sigma 2, or have an error within it as sigma 1, sigma 2, sigma 6. So what we are talking about is sigma 1 being a measurement of what the error, or that's what the variance within each sensor is. We will make this a little bit more mathematically formal when we go to the statistics portion of the course. But this accounts for the fact that not all sensors are equally reliable. Now, why does this matter? This matters because, see, I am saying that how a measure of how good or bad our model is dependent on the gap. Now, let's just say that one was a really good sensor. A huge gap here should actually be weighted hugely. Okay, so you want to give a lot of emphasis to that. Okay, whereas a small gap in a good measurement device might mean that even that gap could be amplified by a lot. Or a big gap in a measurement device which is less accurate doesn't have to be, oh, that person is, or this sensor has always given a lot of error. So maybe the fact that the model and the truth are very different need not be given so much emphasis. So what the sigma does is gives different emphasis to different sensors. But to start with, okay, we will come to what is known as weighted linear regression, which gives this different type of emphasis later. But to start with, we will assume equally accurate sensors. So that means we are going to assume sigma 1 equal to sigma 2, so on and so forth, up till sigma m equal to sigma. Okay. So now we can define one new quantity, r square. I'll again tell you what this means. This is equal to sigma square times r prime square. And that's just going to look like sigma I equal to 1 to m yi minus y hat I square. So this is simply the sum of squares of the error. Okay. This r square, this r is called the residual. Okay. R stands for residual. Why have we put square? Just to emphasize that this is actually a positive quantity. Now, there are two names that I'm going to use, one or the other, depending on the notation. So within the inverse community, this R square is typically called S. S stands for sum, as you can guess, sum of residuals. And this is equal to sigma I equal to 1 to m yi minus y hat I square. Now, another name which is more common within the machine community, machine learning community, is J. Okay, so J is called the cost function. I'm not sure why this letter J came. Maybe it starts with German or something of that sort, or the loss function. All that means is what is the cost of the fact that your model and your reality are different. So J is mean. Okay, so the mean measurement I equal to 1 to m yi minus y hat I square. Okay, so this is basically S divided by m. This is called the mean squared error. All of you would have seen this at school or even at college. Also sometimes called which as MSE, standing for mean squared error. So J is the cost function or the loss function. What do we want? Okay, so our model, so the best model to solve the inverse problem is the one that minimizes J, okay, or S. S is simply one factor, the number of measurements multiplying J. So the best model is the one that minimizes J. Now, what are the parameters that we have within J? So this means we need to find W0 and W1 that minimize J. And remember, J is simply the sum of the square of the error. Now, if you look at it only in this form, it might look odd. I mean, you want to find out W0 and W1, which minimize this, but where are W0 and W1? Where exactly is W0, W1 in this expression? So let's make that explicit. So note that W0 and W1 is actually hidden within here. Yi hat, our model, is W0 plus W1 times Xi. What does that mean? Let's go back to our example once again, which is why we introduced this first. We are saying that this here is Y, this is X, this is, for example, X1, X2, X3, Y1, Y2, Y3. Y, remember, is the truth or the experimental temperature. Corresponding to this, we should have a Y hat, which we will see in the next video. We'll see the actual values here. But suppose I guess that W0 is 0 and W1 is 1, then the model would have said W0 is 0, W1 is 1, then Y hat is W0 plus W1x. In this case, that will be 0 plus 0.1x, 0 plus 1 times 0.01. So this will be 0.01. Okay. So on and so forth. So if we take this model, this will become 0.02, 0.03, etc. As you can see, the gap between Y and Y hat is huge. This is not a great model. Okay, but that's just to tell you how Y hat is calculated, and Y hat itself depends fully on W0 and W1. Okay, so Y hat is a function of W0 and W1. So please remember this as we go forward. Okay, so Y hat is a function of W0 and W1. All right, so we want to minimize J. I'll put the mathematical language for this in the next one, but for now, let's use a sort of casual language. So J depends on W0 and W1, and it's given as, I should have put 1 over M here, 1 over M Yi minus Y hat I square, where Y hat I equal to W0 plus W1 Xi. Okay, so this is equation 1, this is equation 2. Now, when we have two variables like this, W0 and W1, and we want to minimize J, so min of J is achieved when del J del W0 is 0 and del J del W1 equal to 0. If you do not recall this from your multivariable class, then I'll be doing this sometime later during the course, maybe around the 7th or 8th week. I'll be again kind of deriving or giving you some physical intuition, but at least from one variable calculus, you know, if there was only one variable, then it should be dj dw equal to 0. If there are two variables, it turns out that both the partial derivatives have to be 0. Like I said, the geometric intuition for this I will talk about later, once again towards the the third half of the course, or the third part of the course or so. Okay. So now let us see if we can differentiate this equation and get these terms. What are the terms that correspond to del J del W0 and del J del W1, or what are the equations that correspond to this? Okay. So del J del W0, you notice this is J written simply as a function of Y hat. This is Y hat written as a function of W0 and W1. So we can differentiate this in two steps, and that turns out to be the easiest way of doing this. So del J del W0 you can write as del J del Y hat multiplied by del Y hat del W0. Okay. We want to set this to 0, but let us first start with this equation. Now, a convenient thing that we can do just to do this del J del Y0 is to put a factor 2 upfront here. It's not very important, but typically we do that. We put a half so that when we take a derivative, this 2 and 2 cancel out. So it's a little bit easy. So instead of taking mean square error, we take half of mean square error. That's just a convenience that we use. Okay. So if we do that, what does this come to? Okay. So if you do del j del y naught, y hat. So I am going to take a simple example and then extend it. So let us say, instead of having this summation from 1 to m, I have a simple equation. So instead of this, I'm just going to do j equal to half of the sigma I am going to erase out and simply going to keep as if it was just y minus y hat square. And I'll tell you how to extend it to the general case shortly. Okay, so now if I do that, then del j del y hat simply becomes, this square comes down here, half into 2 into y minus y hat into derivative of y hat minus y hat with respect to y hat. So there is a minus 1. So I hope this is not too complicated for you, but you should be able to do it fairly straightforwardly if you wish to do this course for credit. Okay, so this is a simple derivative. Del j del y hat is y hat minus y. So I'll write that here. Del j del y hat equal to y hat minus y. Okay. Now, what about del y hat del w naught? Remember, y hat equal to w0 plus w1x. Okay, I have dropped the i's as you can see, but it's just a convenience. So del y hat del w naught is simply equal to 1. So we now have this del j del w naught equal to y hat minus y. Now suppose I bring this sigma back, which I dropped. Okay, the sigma here. So this would be for just one term. So if I am just taking the first term, this would be y hat 1 minus y1. Another way of looking at this is like this. Okay. So suppose j equal to summation of 1 over m ji. Okay, where ji is yi minus y hat I squared, and I'm going to keep a half. Okay, all I have done, if you look, compare the expression here and here, is I have just added a subscript. Okay, and the summation is moved here. Then I know that del j del w naught is 1 over m summation of del ji del w naught. Okay, and we now know, based on our expression so far, that del ji del w naught equal to y hat I minus yi. Okay, because all I have done is just replace this j with a ji and y hat with a yi minus yi. Okay, once we do this, we basically get del j del w naught is 1 over m sigma I equal to 1 to m. This now becomes y hat I minus yi, which we just saw, y hat I minus yi. Okay, so this we will keep as equation 3. Now, suppose we do the same thing with del j del w1. Okay, so I'll do the same trick again. Del j del w1, I'm going to call it del ji del w1 equal to del ji, or let's drop the i's for now, just to keep the whole thing a little bit manageable. Del j del w1 is del j del y hat del y hat del w1. Del j del y hat we just calculated, as you saw here. Del j del y hat is simply y hat minus y. So we are going to call this y hat minus y. And y hat was our model, which was w0 plus w1x. So del y hat del w1 is equal to this, the derivative of this with respect to w1 is simply x. So this is going to be x. So we can now write this down as del J del W1 equal to y hat minus y times x, except when we actually do this, just like the last time, you will get a summation. So the summation will be from 1 to m, I equal to 1 to m, y hat I minus yi xi. So this calculation here was just for one sensor. This is the full calculation. So let's call this equation 4. Okay. So you can notice equation 3 here is for del J del W naught. Equation 4 here is for del J del W1. For minimum, J, we need del J del W naught equal to 0 and del J del W1 equal to 0. So let's put these two equations in play. So this first condition will say sigma, I am going to eliminate the divided by m's, sigma y naught y hat I minus y equal to 0. Let's call this equation 5. And the next equation is going to be sigma of y hat I minus yi times xi equal to 0. This is equation 6. There should be an I here. Okay. So these are the two equations. Now, by the time you come to these two equations, we might forget what it is that we are looking for. So we should remember what it is that we are looking for. In fact, let's retain the m. Okay, so that might make things a little bit more convenient for us in a little bit of time. Okay, so these are the two equations, and we want to solve these two equations for what were our unknowns. Our unknowns are find W0 and W1 that satisfy equations 5 and 6. Okay. That is really what we are looking for. All right. So at this point, you might think, what is the meaning of these two equations? So what is the meaning of equations 5 and 6? And how do we proceed in solving for W0 and W1? So let us look at that in a short way. What does this mean? Okay, so what does this first thing mean? This simply means that the average error of the best model is 0. This is what this equation means. You notice this is the error, and that's why I retained the m. What this says is the average error of this model is 0. This one says that the weighted average by x is also 0. This one has a harder meaning, but at least let's look at the physical meaning of the first term. The first term here, if you notice, is looking like this. So suppose this middle red line is our model, you will see that somewhere the error is positive and at the other places the error is negative. Whereas the bad models are all on one side. Okay. So at least we have a physical intuition that a good model should go on both sides of the truth. And that's the intuition that this equation here is re-emphasizing. Okay. This, on the other hand, is a little bit harder to interpret, and we will see that in the next video. So let's see how to solve these two equations. Remember, we are looking for W0 and W1. So equation 1 is 1 over m sigma. Now y hat I is simply W0 plus W1 xi minus yi. Okay, remember yi is the truth, xi or the actual temperature. This is the location of the sensor, and these two are the parameters we are trying to solve for. It's useful to just remember what we are solving for throughout. Okay, so this is 0. This is equation 5. Let's just continue with simplifying this. This summation is from I equal to 1 to m. W0 is a constant with m. The only thing, or constant with I, the only thing that depends on I here is xi as well as yi. So now if we look at the first term simply is sigma of W naught, which is a constant which you can take out. So this is W naught times sigma I equal to 1 to m. I'm just doing it term by term. This just becomes 1, the whole thing divided by m. Okay, I'm going to take each term. Then W1 terms times sigma xi I equal to 1 to m, the whole thing divided by m. And the final term is minus sigma yi I equal to 1 to m. Let's just assume that 1 to m is 0. Okay, now let's look at these terms one by one. Again, the first term is simply W naught. Sigma 1 from I equal to 1 to m is simply m. So m by m, so that's 1. This is W naught plus W1. Let's use some terminology. This is the average value. So if you see sigma xi I equal to 1 to m, 1 over m, this is the average value of xi. So the average location across the domain. So we are going to denote this average by a bar. Okay, so x bar denotes average value of x over the domain. Okay, so W1 times this term becomes x bar. Minus this term, now you can see, is the average value of y. So we will denote this by y bar. Okay, so now you have an equation. I'm going to write this compactly. W0 plus W1 x bar equal to y bar. Okay, so notice this. This is one equation. Notice how nice it looks also, because it tells you at the average location, I should accurately predict the average output, or in this case, the average temperature. So this equation actually has a physical meaning. Okay, so this, let's call this equation 7. Now let's simplify the next equation, which was equation 6. So equation 6 is here, this equation. So I'm going to write that down. 1 over m sigma y hat I minus yi multiplied by xi equal to 0. So you can see it is exactly the same as the previous equation, but like I said, it has a weighted weighting here, xi. Okay, so we will open this up. Y hat I is w0 plus w1 xi minus yi multiplied by xi sigma. I'm going to drop the 1 to m just for keeping our notation a little bit compact. So same thing. The first term is W naught sigma 1, the whole divided by m. Sorry, I made a mistake here. Sigma xi. Okay, so W naught times xi. So W naught can be taken out. So W naught sigma xi divided by m. The next term is W1 sigma xi square divided by m. And the final term is sigma xi yi divided by m. This whole thing equal to 0. Okay, so now let us do the same interpretation that we did the last time and write this down. So the first term becomes W naught times this combination of terms. So that's simply x bar. You can say sigma xi divided by the average value of x plus W1 times, now this is the average value of x square. So the square, the location is what we are averaging at this point. So this is x square bar. Now it is important to note something here. This is a mistake that students often make, or people often make. X square bar is not the same as x bar square. What is the difference? This is the average of the squares. and this is the square of the average. Okay. So for example, if you have the numbers 3 and 5, then x square bar would be 3 square plus 5 square by 2. So that is 9 plus 25 by 2, 34 by 2, so 17. Okay. Now x bar square is, what is x bar? X bar is 4. The average of this is 4. So this is 4 square. So this is 16. So you can notice x square bar is not the same as x bar square. So what do we have in this term? This is x square average. So that is x square bar. So please do notice that. It's easy to get confused by this term quite easily. Okay. So minus, you see this term here. This is average of xi, yi. So this is xy bar equal to 0. Okay, so again, the same thing holds true here too. Also note that xy bar is not the same as x bar, y bar. This is the average of the product, and this is the product of the average. These two are not the same, and we'll see this in greater detail when we come to the probability portions of this course. Okay, so we can put this together and write an equation. W0 x bar plus W1 x square bar equal to xy bar. Okay, so this we'll call equation 8. Just for your recollection, equation 7 was W0 plus W1 x bar equal to y bar. Okay, this was equation 7. I'm just rewriting here so that it sits on the same page for you for easy reference. Now notice this again. This is a useful thing to remember. This is called taking moments. Unfortunately, we won't have the time to discuss this in great detail within the course. This basic equation, if you remember, you can generate this equation fairly easily. So this equation is just W0 plus W1 x bar is y bar. All I'm saying is this is coming from the model. Remember, okay? So this comes from the model. So what it is saying is y hat at an average location should be equal to the ground truth, okay, averaged. Okay. So from there, if you just multiply each term notionally by x bar, or you first multiply each term by x and take an average, you get this equation. Okay. So you can see y bar becomes xy bar, x bar becomes x square bar, and 1 becomes x bar. Okay. Now we have two equations and in two unknowns. And we can solve this to obtain W0 and W1. Okay. So fairly easy to do that. So the way to solve this is, let's say we eliminate W0 by multiplying equation 7 by x bar and subtracting out equation 8. Okay, so x bar multiplied by equation 7 minus equation 8. So what that gives you is W0 x bar plus, now notice, W1 x bar square, okay, equal to x bar y bar. This is the right hand side. And now you subtract out this equation's terms, which are W0 x bar plus W1 x square bar. So this is where the distinction between x bar square and x square bar becomes important. On the right hand side, you subtract out x y bar. So these two terms cancel out. So you get W1 times x bar square minus x square bar equal to x bar y bar minus xy bar. Okay. So you can now write W1 equal to, I'm going to reverse the signs because that's the usual way in which it is written, xy bar minus x bar y bar divided by x square bar minus x bar square. So this is the analytical solution for W1. Of course, we need W0 also, and we know that W0 plus W1 x bar equal to y bar. So this gives us W0 is y bar minus W1 x bar. And you can write this in a convenient way. W0 becomes x bar multiplied by xy bar minus y bar times, I'll leave the derivation up to you. It's a fairly straightforward derivation, divided by x square bar minus x bar square. Okay. So this is the analytical expression for W0. So put together, these are the coefficients of the linear fit of a linear model in one variable. So this, my very specification here, tells you a few things. We have automatic questions that will come from here. Okay, what happens if my model is non-linear, or let's say it is quadratic? Okay, so when would it be quadratic? For example, in case I have something with heat addition. Okay, so you could have, instead of a linear model, you could have a quadratic model there. What happens in that case? Okay, what happens if it is cubic, quartic, etc., etc.? What happens in general if it is non-linear? We were able to find out these formulae in case of W0 and W1. What if it is non-linear and it's very messy? Then what do we do? Okay, the next question is, instead of one variable, because I was doing in only one dimension, what happens if there are multiple variables? So what do we do for such cases? Final question that we have is, what is the accuracy of this model or of this process? How do we know? Is this the best that we can do? Can we do something else? Maybe we fit a line here just because physics said it was a line. What if we fit a slightly different model? Maybe physics is something else. So all these questions we will answer in the future videos within this week. So in this video, all we saw was two simple expressions for W0 and W1. Usually these equations are written a slightly different form, which I will discuss in the next video. But more importantly, in the next video, we will also start with the quadratic model. We will also look at how you can generalize the same process if you have multiple variables. So thank you. That's it for this video.